In the previous section of the book, we learned about moving averages. Now, moving averages are used as a first step of what we're going to learn about in this chapter, which is classical decomposition. The method originated back in the 1920s, and it still forms the basis of many of other decomposition methods. So it's important for us to learn. It's a very simple method. It's not hard to understand what happens here. So there's two types of classical decompositions that we can perform. One is the additive decomposition, where our components add. So our trend component is added to the seasonal component, is added to the remainder component. Or a multiplicative decomposition, where these interact in a multiplicative way. So T times S times R. Now, decomposition is the effort of estimating these components. Okay? What happens with classical decomposition? Well, the first step is to actually use moving averages to get a trend cycle estimate, get an estimate of the trend cycle component. Now, we start off by saying that if M is even, we're going to use a 2 times M component moving average, hence a centered moving average. And we start off with this because when the method originated, most of the data available would have been monthly or quarterly data. Higher frequency data was very rare back then. Otherwise, if we do have higher frequency data, if we do have daily data, for example, then use a 7-component MA. So if you do have a data with periodicity that is odd, use an M times MA component. So in the first step, we compute the detrended series by removing the estimate of the trend from our data. So YT minus T, the estimate of T, the trend cycle component, will give me the detrended series. If I'm performing an additive decomposition, if I'm performing a multiplicative decomposition, then YT divided by my trend cycle component will give me the detrended series. Now, we've removed the trend cycle, the smooth TT, from my data, and that will leave behind the seasonal plus the remainder. So the next step of this is to estimate the seasonal component. How do we estimate the seasonal component? Well, very simple. The seasonal index for each season is estimated as an average of the detrended series for that season of successive years. So basically what we're going to do is grab all the Januaries in monthly data and average those, and that will give me a seasonal index for January. Do that for February. Do that for Q1 if you got quarterly data, or Q2 if you got for Q2, and so on. Now, if necessary, we can adjust these so we can have them equally. We can have them constrained so that in an additive decomposition, these seasonal indices add to 0. In a multiplicative decomposition, these seasonal indices will add to M. So basically, what we do here is to sum these up and split out the difference. So you spread out any differences if you want, so that they can sum up to 0 if it's additive, or they can sum up to M if it's multiplicative. Now, the seasonal component S simply consists of the replications of the seasonal indices. So once we have the 12 seasonal indices for monthly data, we repeat that over the whole time series. If we have the four indices for quarterly data, these are the ones that are repeated over the time series for the seasonal component. So once we have the trend cycle and the seasonal component, subtracting these two from the data will leave us the remainder. If we have an additive decomposition, of course, we have to divide through these two components to get the remainder from multiplicative decomposition. Hence, very simply, classical decomposition is what I just described to you. So we choose an additive or multiplicative depending on which gives the most stable components. Okay, so if we think we need a multiplicative decomposition, we'll perform a multiplicative decomposition. If not, we use an additive. For multiplicative model, this method is also known as the ratio to moving average method. Here's an example using US retail employment data. This is the number of people employed in US retail. So our original data is monthly, and you can see strong seasonal pattern. Here's the trend of, here's an estimate, of the trend cycle component, a smooth trend cycle component. Here is now the seasonal indices. So the seasonal indices is, once I've subtracted this from this, I would get seasonal plus remainder, take the averages of all the Januaries, that will give me the seasonal index for January. For January, that's the first month here, and so on. The spikes here, this is US employment data, so the spikes here would be the summer months, June, July, August in the US, in contrast to what it would have been in Australia. Once we get the seasonal indices, we subtract the trend and the seasonal indices from the original data, and that will give us the remainder. Notice here notice the scale here of our components. So the scale of our trend cycle component is in the same scale as our original data, and to this will be added, the seasonal component will be added the trend component. In a multiplicative decomposition, the scales here for the seasonal and the random or the remainder are different in that here, these scales show you by how much you would inflate your level to get back to the original time series. So if we take this observation here, which may be the June one, then we need to multiply this observation by 1.04 to get the data here, and also by 1.05 to get the data here, okay? So remember, in a multiplicative decomposition, we have LT, or TT, sorry, the trend cycle component times ST times the remainder. How do we do that in R? Very simply, we use the model function. We tell it what decomposition we want to do. We want to do a classical decomposition. The data that we're going to use is the employed series out of the US retail SIBL. We tell it what type of decomposition we want. We want an additive decomposition. From there, we can extract the components and we plot those. And that's how we get these graphs here. So that is the additive decomposition. If in this code I had a multiplicative type, then I would have gotten this graph. To wrap up, some comments on the classical decomposition. Well, as you notice, the estimate of the trend is unavailable for the first few and the last few observations. Okay, let's highlight that again. And we all know now why that is the case. Using moving averages, as we saw in the previous section of the book, we cannot get estimates of the trend for the endpoints of our time series. The seasonal component repeats from year to year, so maybe this is not realistic. There's cases, and you'll see examples, where the seasonal component may change over the years. One classical example is with electricity demand, where we have peak electricity changing from winter seasons to summer seasons as air conditioning is being introduced wider in a community. Also, it's not robust to outliers. So the decomposition relies on averages, and averages are very sensitive to outliers. A huge outlier will move that trend quite rapidly, quite significantly. So newer methods that we're going to learn in subsequent sections of the book have actually found ways of overcoming these limitations.